In this segment, we're going to talk about some of the problems with sequence-to-sequence models. And the reason we're going to do this is it's going to build us towards this idea of attention, which is probably one of the most important innovations in making this stuff actually work. And we're going to see that it underlies the transformer architecture, which then leads to pre-trained models like BERT and GPT. And I think it's not an exaggeration to say it's one of the biggest innovations in NLP in the last decade, really. So let's start off by talking about the motivation for this attention piece by looking at some of the problems with Seq2seq models if we just implement them in the framework we've described so far. So encoder-decoder models, when you build them, they like to repeat themselves. So if you have the sentence, un garçon joue dans la neige, we might have a Seq2seq model that says a boy plays in the snow, boy plays, etc. And it'll just keep generating these two final tokens. So this is usually a sign that the model's a little bit undertrained. And so if you train the model just right, it's not going to do this. But this is something that we can see happen from these kinds of models. And why does it happen? One reason is that if your LSTM state isn't quite right, if you're doing this with RNNs, you can kind of get stuck in a loop where it'll generate an output token, feed that in as the next input, generate another token and feed that in. And basically based on the tokens it's seeing, it's just sort of iterate, either generating the same thing repeatedly or you kind of repeating a short phrase in this fashion. So the idea from machine translation that has typically, which we'll talk about later when we get to MT for real, but the idea from MT that has typically solved this is a notion of coverage. You should translate each word once. And that's something that we haven't encoded yet, but would be very useful to do. All right, another challenge is that these models don't scale well. So first of all, they don't generalize to longer sentences. So if you train them on sentences of length 10, they're not going to work well on sentences of length 20. And then also they just start to break down once you get into longer sentences in general. You have to increase the size of your representations because your fixed size hidden in cell states don't scale. And LSTMs, as much as we talked about them being an improvement, they still don't remember information for arbitrarily long periods of time. And so these are some results from the work of Badenau et al., where they show that the BLUE scores, which is a metric for evaluating machine translation output, decrease dramatically once you start to go to longer sentences. And their top line here that doesn't decrease is a model that uses this attention mechanism. So this is going to help us combat this problem of, having this fixed size representation that doesn't scale and not being sure what to do there. All right, so the final problem I'll bring up is unknown words. So if we have words in our input like ecotax, pont de buis, etc., these are often pretty hard to encode correctly into a vector space. Now, if they're straight up unknown, we just have no embedding for them. And even if we do have an embedding, if they're a rare word, it might not get kind of put into the hidden in cell state vector correctly. And it's going to be hard to thread that vector all the way to the output, right? But, it's like we're doing a lot of work we don't need to, because pont de buis, it's like we see this string and we know that we should just copy this string into the appropriate place in the output, right? So like, why are we kind of mapping it into this intermediate representation and mapping it back out when we could just be having some sort of copy operation? So let me tell you something that would solve these problems, but it's sort of a too strong assumption. If we knew that we were doing a word-by-word translation of our input, then what we could do is we could look at the corresponding input word at each point in the decoder. So what I'm talking about here is, suppose we fed in "the movie was great" into the decoder as an additional input, in addition to the previous decoder time step that we're already feeding in. then this translation problem actually looks really easy, right? Because we're not only seeing the context word, but we're actually seeing the word that should directly be translated to this time step. So all the model needs to learn to do is to take movie and map it into film. And this is much easier than remembering that it saw a movie 6 time steps ago, and now at this point in the LSTM decoder, we've seen this word and it should generate that. This is much easier, right? And so it removes a lot of the burden on the hidden state to do this complex modeling, and so this would generally be pretty cool. On the other hand, this aligned inputs assumption is a little too strong. So we'd like to be able to do this, but not encode it in some super rigid fashion. And so that's going to be the idea of attention, where what we are going to do is at each step in the decoder, we are going to predict a distribution over positions in the source sequence or the encoder sequence. And then we are going to use that distribution to help predict our output token. And so in this case, for example, the fact that the distribution assigns high weight to that's assigning high weight to a particular location in the input. And we're going to look at the kind of embeddings at that location and use them to help make our decision. And then ideally, the model should kind of move its sort of soft pointer over to movie and then predict the right word there. And so at each decoder state, predicting this distribution is going to allow us to look back at the input much more directly. It's going to achieve the same idea as this aligned inputs model, and it's going to do this in a smart way based on the current decoder state. So we don't need to hard code in a rigid assumption here, but it's going to flexibly learn how to do this, and this is going to kind of greatly upgrade the power and flexibility of our model. That's the end of this segment.